4 stages, 4 components. Let's get to it.
Stage 1, the evaporator.
Stage 1, evaporation. This is an air source heat pump evaporator, the first part of our cycle. Now, this evaporator is, for all intents and purposes, a heat exchanger. It's going to take thermal energy from outside, the air that surrounds it, and it's going to transfer that air into our central heating system. This is where the term free energy comes from. Now, it does that with some support from some other components that we'll come to shortly. Now, the heat exchanger or evaporator itself is a series of pipework that contains a refrigerant. Now, that refrigerant, when it is cold, can actually be in a liquid state. But before we exchange it to the next part of the cycle, which is compression, we need to make sure that it is in a gaseous state, that it is a vapor. Because what we are going to do in the second stage that we'll come to is we are going to squeeze it. As we squeeze it, we increase the temperature and the pressure of that refrigerant. But we can't compress a liquid. We can only compress a gas. So it's essential that it leaves the heat exchanger in a gaseous state. We actually refer to it as boiling the refrigerant. Now, don't be confused when we think about boiling. The first thing you think about is a kettle and water, which is a natural comparison to make. Refrigerants don't boil at 100 degrees. The refrigerant that was contained within this heat exchanger, which is R32, and we'll cover refrigerant a lot in the book and in the videos moving forward, actually boils at minus 25. So it could be in a gaseous state even at sub-zero air temperatures outside. The thermal energy from the air outside is driven across the heat exchanger to boil that refrigerant. It stays a relatively low pressure, but is then ever so slightly superheated before it enters the second stage. Now, the air outside, unless it's blowing a gale, is pretty latent. There's not a lot of movement. So the support that the evaporator needs to drive that energy through the heat exchanger and across the refrigerant is delivered by our fan. So the fan motor drives the fan impeller. The fan impeller sits in front of the evaporator and pulls that air in across the evaporator, taking the thermal energy from the air and expelling chilled air out the front. It's a very simple process, but extremely effective. The larger the evaporator, the bigger the heat exchanger, the more energy that we can extract from the air outside. And you'll see that when we look at our monoblock later on.
Stage 2, compression. So stage 1, evaporation, was all about pulling the thermal energy from the air surrounding our heat pump, driving it across our heat exchanger, where we move on to stage 2. Our compressor is probably the hardest working part of our air source heat pump, and probably the most greedy when it comes to electrical consumption if it isn't treated considerately. The gas that leaves our heat exchanger is at a relatively low pressure and low temperature. It's drawn into the compressor, where within this hermetically sealed casing there are 2 scrolls. One of those scrolls remains stationary while the other orbits and offsets around it. As the gas is drawn in, those scrolls within the compressor will squeeze that gas, elevating both its temperature and pressure. When it leaves the compressor, it is now superheated and superpressurized, where it moves on to the third stage. We want our compressor to work as economically as possible. We want it to get up to speed and then just keep dripping energy to the third stage. When a compressor completely starts, stops, stops, what that does is it consumes a hell of a lot of energy, and we want to avoid that. So we need to treat it considerately. I mean, think about your fridge and the compressor that buzzes away in the background I can hear just now in my fridge. When was the last time you turned your fridge off? When was the last time you serviced your fridge? When was the last time it broke down? What I'm getting at is these are very, very reliable, but we can't ask too much of them. We need to treat them properly.
Okay, cool. So we have now covered 3 stages of our heat pump cycle. Stage 1 was evaporation, our outdoor heat exchanger that drives and extracts that heat energy from the air outside, transfers it to our refrigerant, converting it from a potential liquid to a gas and giving it a sort of preheat. Where that refrigerant leaves the heat exchanger, the evaporator, to the second stage, which is compression, we now squeeze that refrigerant, squeezing the molecules tightly together, creating a disruption, a kinetic energy. That disruption and kinetic energy increases both the pressure but also the temperature of our gas. How we actually create that pressure is by creating a resistance with our expansion valve, the 4th stage. What we haven't covered is the 3rd stage, which is condensing. Condensing is basically extracting that heat energy from our refrigerant and passing it into the radiators or underfloor system in our house. It's another heat exchanger, but unlike our evaporator, we are now transferring or giving up energy. The refrigerant that is superheated and high pressure that leaves our compressor enters our heat exchanger, our plate heat exchanger, where it comes in contact with our water that goes into our radiator system. The plate allows it to separate, so there's no mixture physically between the two medium. As our central heating pump pumps the water around our central heating system, it pulls the heat energy from the superheated refrigerant and transfers it to our house. As the refrigerant passes through the heat exchanger, it's still a high pressure, but it's now starting to lose temperature. It's giving off its energy to our central heating system. As it leaves the condenser, it's now a much lower temperature, but still a high pressure. And how we alleviate that pressure is again back down to our expansion valve, which then throttles opening and closing all the time to control that pressure before it goes back to the evaporator, where it picks up that thermal energy again from the air, this free energy, and we start all over again. Simple but effective. Expansion. So when our gas leaves our heat exchanger, remember at this stage it's a relatively low pressure and low temperature. It's drawn into our compressor, where the second stage compression squeezes that gas, crams the molecules within our refrigerant tightly together, where it forms kinetic energy. A byproduct of that kinetic energy is temperature. So when the gas leaves our compressor, it's now a high pressure and a high temperature. That's extremely useful. But if we are trying to cram and squeeze that gas together, we need something that fights back. If we're squeezing against an open door, then there's no resistance to elevate that pressure. And if we can't elevate the pressure, we can't get the molecules tightly together, and we can't create this temperature, which is essential because ultimately we need the gas to heat up to get the heat into our home. So the third stage is our expansion valve. This is an electronic expansion valve that can modulate and throttle pressure and movement. So when the compressor starts up initially, the expansion valve will resist the flow of refrigerant through the valve. As it resists it, that pressure can start to grow. As the pressure starts to grow, we can start to develop this temperature. Once we've got the cycle actually moving and creating this kinetic energy that we need, the expansion valve will react to the outlet demand of our heat pump and modulate that flow. It can also dissipate the pressure by opening up and relieving that pressure when required. So it's a very essential and clever part of our cycle. This electronic expansion valve can modulate to anywhere between 400 different positions of modulation. Within the hermetically sealed casing, there is a spindle that will move, open and shut to demand. This is sent by a magnetic pulse head, which basically turns the valve inside based on that demand from the heat pump. Clever stuff. So the 4 stages of our cycle: evaporation, compression, condensing, and expansion. These are consistent with any type of air source heat pump that we utilize. The cycle does not change. So if those 4 components are the main stars in our heat pump performance, we need to give special recognition to another component in that cycle. This component is our 4-way valve. Personally, my favourite part of the heat pump cycle, because I'm a bit weird like that. A 4-way valve can deviate the process and the cycle by reversing the whole cycle. It can actually send superheated refrigerant back through our evaporator to defrost it in cold conditions. In modern times as well, it's also been used as a form of cooling, where as opposed to putting superheated refrigerant into our condenser, we can actually put chilled refrigerant into our condenser to send chilled water into our house. Now that sounds a bit counterproductive, but when used with heat pump convectors, they can actually create a cooling culture within your home. So your heat pump can heat your house in the winter, but cool it in the summer. It's a real piece of engineering and my personal gratitude to it, because I think it's a fantastic bit of kit.